Okay, should be fine. Okay, these two equations are the most two equations we have for this chapter. So let's read through them once again. So first we have the inverse Fourier transform, which says that x of t equal to 1 over 2 pi, integration minus infinity to plus infinity, big X of j omega e to a j omega t d omega. And then we have big X of j omega equal to integration minus infinity plus infinity x of t e to a minus j omega t dt. And I have seen that this is those two equations are analogous to the synthesis equation and the analysis equation in our Fourier series representation. So this inverse Fourier transform, we can view this as we are expressing x of t as a linear combination of this e to the j omega t. Although it's not quite the same because we have the 1 over 2 pi factor here, and also since x don't have a fixed periodic, so now we don't restrict our omega to be the harmonic frequencies, so we are integrating over all possible omega from minus infinity to plus infinity. Okay, and so instead of having this discrete series for different, so this coefficient ak for different k, where k is the index for your harmonic series, we are integrating over all possible omega, and we just have this big X over j omega function for every omega from minus infinity to plus infinity. And also, I guess we see that here this is a kind of funny notation here because we write big X over j omega. So you might think that in chapter 3 we just have a sub k where k is the index here. And here this x of j omega is a function of omega, and in minus y down we just write x of omega here. And this is because we want this notation, but this notation makes sense. We'll see in chapter 9 that we write this as big X of j omega, so that this notation is consistent with the Laplace transform. Okay. And anyway, so that's kind of like a synthesis equation for Fourier transform. Then we have the analysis equation where we calculate how to get the big X of j omega for a particular x of t, then it's this equation. Okay, and also remember that we derive this from taking the from having the Fourier series representation and taking a limit of big T equal to infinity. I guess yeah, that's the derivation. Take the big T to infinity. And then I think so we go over this very quickly this time. So once again, there are different conventions for Fourier transform, and I guess the particularly interesting one is the middle one. So a lot of people like this notation because you see that it's symmetric with respect to this 2 pi. Yeah, because you see that so you can do mathematics and check that this form is also correct, means that you can transform from small x to big X and big X to small x. And you see that these two forms are more symmetric in 2 pi, so one of the equation have a 1 over square root pi, and another equation also have 1 over square root pi. Okay, so if you write x of t and the big X of j omega in this way, then you see that these two equations are almost the same. You're just swapping x and big X and t to j omega, and get the h1 minus sign here. Okay, but anyway, we will stick to our notation where we have 1 over 2 pi on x of t, which is a bit weird, but this is our definition. Okay. Okay, and I guess to finish kind of the derivation, we will do things very similar to chapter 3. That is, now we need to discuss the convergence. And once again, so I guess this part is very similar to chapter 3. So I will just like in chapter 3, let's state the results. Okay, so just like a Fourier series, sometimes the Fourier transform don't converge, and they will converge in some in some time. Okay. And so our idea of checking a convergence is similar to chapter 3. So we think about this way. So we have this inverse Fourier transform and the Fourier transform. So we start with some x of t, and we try to see whether when we transform from small x of t to big X over j omega with this equation, this equation, then transpose back to another x head of t with this equation. They want to see whether back to the same x of t. Okay. So yeah, so that's the idea. We go from x of t to big x of t, then try to go back to x of t. So if your function x of t is very nice, you should go back to x of t. But then just like in chemistry, we see that this don't always happen. Anyway, so there are two things we want to check. First is we want to check the integration. So there are two integration of infinity here. So first you want the integration to both converge. So you want x head of t to exist on every t, and also you want if it exists, you want x head of t to equal to x of t. Okay, and so one condition that can guarantee that this kind of happening is that the x of t have finite energy. Means that this integration of absolute value square of xt is a finite value, and it can be shown. So we stay with our proof here that if this is true, then we have x of head of t has some kind of convergence to x of t. Okay. And the convergence is not exactly the point one convergence is something that we had before that we say is like in terms of energy they converge. So we have the x head of t and the x of t. We can calculate a difference. So we define some error term equal to x head of t minus x of t, and then we say this is convergent. Then we say this difference function. When we integrate from minus infinity to plus infinity, we say this in the error function is absolute value squared, then we say it's 0. Okay, and so here we have some kind of example. So maybe x of t is not very continuous function. So maybe x of t is constant 0, except at the 0 point it's 1. Okay, so just at 1 point is 1. Then x head of t will be constant 0. Then you see that the difference is only 1 point here, and because this point has no width here, so your integration over the difference square then is 0. Okay, because it's just 1 point, and 1 point your integration through it has area 0. Okay. Okay, so that's a convergence. So I guess the first convergence is that if you have finite energy, then you have that if your signal has finite energy, then the error has 0 energy. And we are going very quickly here. And another thing that we also have are the directional conditions. Okay, so we have a strong form of convergence is if the signal satisfies the directional condition, then we will have this pointwise convergence. So x head of t equal to x of t at any t, except discontinuity. Okay, and the directional conditions are very similar. So yeah, I think so. All three conditions are same, except that previously those conditions are stayed over one period, and now they are over like the whole real line. Okay, whole real line of t. Okay, so x of t is absolutely integrable, and in chapter 3 it was absolutely integrable over one period, and now it's absolutely integrable over minus infinity plus infinity. And x of t has finite maximum minimum, and I guess it's a little different, but it's a finite maximum minimum, and but it's all actually within any finite interval. So over minus infinity to plus infinity, you can still have even number of maximum and minimum, but like I guess the density of maximum and minimum should be finite over any interval, and also the density of the discontinuity need to be finite over any interval. Okay, and before this was only over one period because well it's periodic, so if it's over one period then it's over any finite interval. Okay, and yeah. Oh, and here we have extra condition. We also have that if you that the discontinuity must be finite. Okay, And anyway, here we set the result, and you have some signal, and you can check whether you satisfy all three direction conditions. And if satisfied, then you have this XLT equal to XOT at any t except discontinuity. But just like in the finite in the periodic case, this XLT equal to XOT for any t doesn't guarantee, how do I say, actual convergence, because I guess easier to say there still gives effect, as we'll see. Okay. Yeah. Okay. And anyway, that's the convergence of Fourier transform pair. Any question? We have a very brief introduction here, the state result. Okay. If not, then we will actually close this topic and go to go to some example of Fourier transforms. Okay. So yeah, we just give some signal and let's try to calculate the Fourier transform. And the first signal is this signal we kind of seen a lot, this exponential decay cutoff at t equals 0. So e to the minus at times u of t. Okay. It's like this signal. So e to the minus at is exponential decay with a greater than 0, and u of t will cut off it at t equals 0. And then we just straight up do the calculation. We do the integration here to calculate big X of j omega. So big X of j omega is the integration x of t times e to the minus j omega t dt. So x of t is this thing, and this u of t will cut off your integration from the lower bound from minus infinity to 0. So integration from 0 to infinity is minus at to the minus j omega t. And then you just do algebra. This is you have e to the minus a plus j omega t. So then you have this minus 1 over a plus j omega term, and you have e to the minus a plus j omega t from 0 to infinity and infinity. Then here we use a equal a is greater than 0, because a is greater than 0 at the t equal to infinity. This is 0. So the upper bound term is 0 and the lower bound term is 1. So you have 1 over a plus j omega. Okay. And so x of j omega as a function, well, it's a complex function of omega. And if you plot its amplitude and angle, it will look like this. Okay. And you think this kind of makes sense, because when omega equals 0, this is 1 over a and it's largest. It should be largest, and when omega getting larger, then the number under 1 should get larger, and it gets this decay, and it should decay as 1 over omega when omega is very large. Okay, and then you can also plot the angle here, and yeah, you can also plot the angle here. And the angle, well, this complex number is a plus j omega, so the real part is a, and the imaginary part is omega, and so the angle is basically arctangent omega over a. And you have a minus sign because it is 1 over this number. Okay, so you can plot the arctangent here. Okay, and yeah, so it's Fourier transform this function, and I guess we can discuss a bit about stability. Okay, and so we can also have a different a here. So before we have a being a real positive number, and this can be generalized a little bit. So a can also be a complex number. Okay, and but if we want the Fourier transform to exist, and here basically we want the big X of j omega to exist, then we want the integration to be finite. And for that to happen, what we need is the real part of a needs to be 0, so need to be negative. The real part of a needs to be positive, so minus a is negative. So that at infinity, it's going to go to infinity. So the infinity bound is 0. Okay. Anyway, so you can check the math, and you see that as long as the real part of a is greater than 0, the calculation gets the same, then you get the big S of j omega is 1 over a plus j omega. And yeah, this result we'll see later. This is quite an important result we'll see later, and I guess it's nice to memorize that a little bit. The Fourier transform of this e to the minus at u of t is 1 over a plus j omega, when real part of a is greater than 0. And I guess we can also see that obviously when real part of a is less than 0, then you have an exponential growing function, and so the signal is okay. So I'm going to say something very weird. I'm going to okay. So let's not say a very weird thing. The signal is absolutely integrable, and if the signal is now I'm going to say something very confusing. So sorry, the signal if it's exponential decaying, then the signal is absolutely integrable, and yeah, and then we have the Fourier transform being convergence. And if the A is so I guess let's start drawing. If A, let's draw it here. Let's talk a little bit about convergence. Okay. And so that's for a greater than 0, and we see that if a is less than 0, then our signal look like this is an exponential growing function, and it's not absolutely integrable, and then you don't have a Fourier transform, so you cannot even calculate big X or j omega because this integration will not converge. And also if and then something very confusing is you can say if your x of t equal to h of t for some, if your x of t is h of t for some system, then being absolutely integrable correspond to being whether your system is stable. So if your h of t look like this, then h of t don't have a Fourier transform. Okay. And I guess that's yeah, that's something we'll talk about later, probably after midterm. But yeah, let's start talking, having some example of this first. Okay. Okay. So if h of t look like this, and then the system is stable, then you have the Fourier transform, and it look like this. The system is not stable, and don't have a Fourier transform. Okay. And anyway, then let's go back to just calculating Fourier transform. And next example is a very special function, delta function. Okay, delta function is, well, it's not quite a function, it has infinity, but it's also absolutely integrable, and you have a Fourier transform. You can do this Fourier transform equation, and then find out that x over j omega is actually a very easy result. So you do this integration of delta times e to the minus j omega t. Then by the shifting property of delta of t, then you just have e to the minus j omega 0, and that's just 1 for any omega. Okay, so you see that you have a very divergent function, and your Fourier transform to a very simple function is just 1. It's a constant function 1 everywhere. And we have this Fourier transform pair of delta of t Fourier transform to 1. Okay. And yeah, so that's a very nice result, and also from this nice result we see something very funny. Okay, so we see that when we reverse this, so now we use this reverse Fourier transform equation, inverse Fourier transform equation. Then we got the result that so if you try to transform this 1 back to delta of t, then this one side you have 1 over 2 pi integration, and then big X is just 1, then e to the j omega t d omega equals to delta of t. So yeah, so in here you find out that this integration of e to the j omega t, this should really not converge. This should feel like a yeah. So this is a really weird thing. This is integrating oscillating infinite oscillating function. So this integration over a periodic function, it should really not converge. But by this Fourier transform pair, inverse Fourier transform and inverse Fourier transform pair, then we think mathematically that we want to define this integration of minus infinity to plus infinity to j omega t d omega. This thing should actually equal to 2 pi delta of t. Okay, and yeah, so although you run this integration in its if you run this integration in its there's a straightforward definition, it doesn't make much sense, because it should be, you think it should be kind of undefined for any omega, but this is actually what we think is true almost always as I guess as a mathematician, because we believe this Fourier transform and the inverse Fourier transform pair. Okay, so yeah, we have this integration of minus infinity plus infinity e to j omega t d omega. And I guess this is one of the pretty easy way to reason that this integration should look like that. And if you want, I guess, more insight and reason on this, then you can take some complex analysis case. Then yeah, complex analysis course. Then they will talk about how this contour integral actually makes sense, etc. And I guess we will also touch this a little bit at the later part of the course. But yeah, this is a nice relation to know. Integration of e to the j omega t d omega. Okay. And yeah, so this is this example. And anyway, so this is nice to know, but this pair we should remember. So delta function is the Fourier transform pair to 1. Okay. And the next example is our our favorite example, familiar example is this block wave. Okay, I guess now it's not quite block wave; it's just a single block. So our XOT is this finite square here. So finite is 1 square here. So from minus t1 to t1 is 1 and 0 elsewhere. This is was our chapter 3 block wave example, taking a limit of t to infinity. And yeah. Okay, and we have this Fourier transform. I guess we actually started the whole chapter with this example, and we kind of already see this big S of j omega. I guess let's try to refresh your memory here. So we start with this example and take in t to infinity, and then we say that our TAK is we say that our TAK will be sampling this envelope function, and we kind of already calculate this envelope function as 2 sine omega t1 over omega. And let's jump back. Okay, yeah, sorry, a little too further. Okay, and anyway, yeah, so we get the same result here by doing the direct calculation with our definition of big S of j omega, and then we see that our previous derivation is still true. So we have minus infinity plus infinity x of t equal minus j omega t dt, and then this x of t will just cut off your integration range to minus t1 to t1, and minus t1 to t1 equal minus j omega t dt. Okay, so this is kind of similar to this thing, but now this is a finite interval, so this is actually a very convergent thing. You can just do the integration. You have equal minus j omega t, then you get like down minus j omega. You have like 1 over minus j omega, and then you do the algebraic. You do like upper bound lower bound with t1 to minus t1, then you will get this 2 sine omega t1 over omega. Okay. Yeah, because you have a finite region here, so this integration is actually finite. So and you have this sine omega over omega term. Okay, so we know our block wave will Fourier transform to this. We'll very soon call this sinc function in terms of omega, because it is sine omega something over omega. Okay, and also as we say, we also have Gibbs phenomena here. Okay. And that means that if we take this equation, I guess here this is the exact convergence, because you see this integration. I don't care about the upper lower limit of x of t. So x of t to big X of j omega, this is exact for your integration. Okay, but when you convert back, then you actually Gibbs phenomena. Means that so you take your synthesis equation and you think about your integration limit. So this is 1 over 2 pi minus infinity plus infinity x big X of j omega equal j omega d omega. And this upper and lower limit, if you take it as some finite value, minus big W to plus big W. If you have this finite W, then you have the Gibbs phenomena where you have ripples at the edge of your block wave that you try to combine back. And yeah, just like before, you take the limit of W go to infinity, the ripple will have finite size. Okay, and yeah, so you see that But you can easily see that this x of t checks all three literature conditions. So it's convergent on every point of t. But just like in the periodic case, the convergence, there is an order limit to this picking t first or picking this w first. So for every w, there is some t that you have finite difference between your x hat and x. And but for every t, there is a w big enough such that x hat equal to x. Okay. So that's a Gibbs phenomena. And now we have something interesting. So this is kind of a hint at something we'll talk a bit more later. That's called duality. So we can actually kind of swap our x over t to big S over j omega. So now if we have big S over j omega now as this block wave, okay, so big S over j omega is a block wave between minus big W to big W, okay, and then we see the x over t has a similar form to this big S over j omega. You do integration, then you see the mass is basically the same. You have 1 over 2 pi integration. Minus omega w to w e to the j omega t d omega. Then you just have h minus sign. You just losing a h minus sign here and get 1 over 2 pi here, and basically you get sin t over t. So this is h 2 1 over 2 pi. So instead of 2, you have 1 over pi, and and the minus sign don't actually change anything, and so you just have bw here instead of t1 here. Okay. And so you see that this signal inverse Fourier transform back to will get the x over t like a sink, and so you see that sink Fourier transform will become a buck wave. Okay, and then but now when you do Fourier transform this way, then you will get Gibbs effect here, etc. Okay, so it's quite funny. And so this very interesting Fourier transform pair. So you have a block wave, then you will get this sinc function, and you have sinc function, you will Fourier transform to block wave, and you can transform back and forth. Okay, and something interesting is we can have a Fourier transform for. I guess this is in this example we'll talk about more general properties. So first we think about. Now we Fourier transform for different value of w, and then we can just look at the correspondence here. Okay, so we have these two correspondence, and so if we make w smaller, obviously this block will get thinner, and we also see that this node here are at the point where you want wt equal to pi. So this point is pi over w. Okay. So the 0 point is pi over w, and so when w gets smaller, then the wave here gets wider. Okay, and this is actually a more general phenomenon for all forms of Fourier transform, and I guess this will later see as a time over frequency scaling. So we see that we squeeze the signal in the frequency domain, so we squeeze the big S over j omega. Then we'll stretch out the time domain signal. So this small x over t will get stretched out. Okay, so this gets thinner, then this will get wider. And other way you can see this get wider, this gets thinner, or this gets thinner, this get wide, this get wider, etc. And then as we say, we'll define this sinc function because it has a nice correspondence to our block wave signal. And so sinc function is defined like this. So it's basically sin theta over theta, but we want better normalization. So we have actually h pi here. So it's defined as sin pi theta over theta. And so this normalization is nice because if you normalize this way, then its height is 1 and it's a 0 point at the integer point. Because the integer sin pi theta equals is pi theta equal to integer times pi, then is sin equal to 0, and the 0 point is taking limit of theta goes 0. This is pi theta over theta, so this is 1. Okay, so sin pi theta over pi theta is a sinc function, and you can express those two functions we had in the previous example as a sinc function with a little different normalization here. So it's a single of omega t1 over pi and a single of pi t or wt over pi, etc. And have different coefficients. Okay. Okay, so that's a single function. Any question? If not, we have, okay, so I guess we are very good. And now we are going to talk about something very funny. So we have said that Fourier transform is, we are generalizing the Fourier series to a periodic function. And they kind of go back to say, actually we can also have Fourier transform for periodic signal. Okay, so this is quite a funny concept because I guess the idea here is that so for periodic signal have Fourier series, but we want to have a Fourier transform to represent anything. So we try to have for periodic signal, we also want to try to write the Fourier transform for that. And we see that we can actually do this because we have basically we have delta function. So we just map our Fourier series to a whole bunch of delta function. Okay, so periodic function, then we see that it has a Fourier series, and the Fourier series can be written as a Fourier transform. The Fourier series can be written as basically so how do I say? Correspond to a linear combination of those impulse functions. Okay, and I guess that's just straight goes into this. Okay, it's a bit easier. And it's basically the idea is here. So the result we want is that because we see the I guess easier to say is this. So periodic function we can read it as a linear combination of the harmonic exponential. That's our Fourier series. And we see that when we Fourier transform those harmonic exponentials, they become delta functions. Okay, we'll derive very soon that e to the j omega t its Fourier transform is 2 pi delta omega minus omega 0. Okay, and the derivation here, so this is very similar to our Fourier transform for delta function. Okay, let's try to go back a little, maybe here. Sorry, okay, yeah, so it's very similar to this thing, but the delta function is on the other side now. Okay, and anyway, the easier way to do this derivation is, well, you don't really want to integration over e to j omega t, although we know how to do it because we already know this thing. But easier way to do is you try to transform from this delta function. So we say if we already know have some signal with big S of j omega equal to 2 pi delta omega minus omega naught for some omega naught. And then we do inverse Fourier transform to find the corresponding x of t. So you integrate, then you just write down inverse Fourier transform formula. So integration this function times e to the j omega t d omega. Then you see that the delta function will just pick omega at omega naught. So you have e to the j omega t here, and the 2 pi cancel with the 2 pi, then you see, so you see the corresponding x of t is e to the j omega naught t. Okay, and and because of this, and before you believe that this function is this function, although it's on frequency domain, is absolutely integrable, then you believe the transform and the inverse transform pair is convergent. Okay, and so you derive this way that this function will inverse transform to e to the j omega t naught t, and now we believe that the e to the j omega t naught t will transform to this delta function 2 pi delta omega minus omega naught. Okay, so it's a delta function position at omega naught with the area being 2 pi. Okay, and so now we have this thing. Then we see that if we have big S of j omega equal to, I guess we can say this in other way. Okay, it's easier. So now we have x of t. The other way is a bit easier to say. Okay, so now we have this Fourier transform pair. then we can write our x of t as a linear combination of e to a jk omega naught t with coefficient ak. This is just a Fourier series representation of a periodic signal. And then now we know that because the Fourier transform is linear, we didn't prove that yet, but it's very easy to see. So because the Fourier transform is linear, so the Fourier transform of this thing is this thing. So corresponding x of j omega is, well, ak is just a linear coefficient, so we have this summation k ak here. And each e to a jk omega naught t transform to 2 pi delta omega minus k omega naught. Okay, so the k omega naught becomes k omega naught here. And yeah, so this is our Fourier transform pair. Okay, so we see that for periodic signal, we can actually write down its Fourier transform because it's periodic, so the Fourier transform is a bit unconvergent, it has some infinity. But if we can allow delta function, then we can write it down. It's a summation of a whole bunch of delta function. Okay, yeah, and so this is the form we got. So x over t equal to summation ak equal to jk omega t, then big x over j omega is the summation 2 pi ak delta omega minus k omega naught. And we can see some example. So I guess let's back to this black wave we've seen a whole bunch of time today. Okay, and go back to actually periodic black wave. So this with 2t1 and period t black wave, and we have calculated before that is ak equal to sin k omega naught t1 over pi k. And from here, then we can directly write down our big S over j omega. So big S over j omega is summation k, and this ak here, and the delta omega minus k omega naught. And it has this picture we've seen before. It's well, it's a whole bunch of impulse delta function. So those impulse, so it has a whole bunch of impulse position at different k omega naught. So for different k, so you have k equals 0, k equals 1, k equals 2, etc. Okay, so for different k, yeah, you have at each k, then you have an impulse at k omega naught. So you see it's equally spaced out because the location difference is omega naught, and they also see that this is the height actually, well, the height is infinite, but the area is taking point at like a sample through this envelope function. That's the Fourier transform of this one block. Okay, it's taking point at this envelope. That's this 2 sin k omega t1 over k. Okay, and anyway, but you see it's a whole bunch of impulse. It's kind of a more complicated example. And then we can go back to either example. So we have x of t equal to sin omega t or cosine omega t. And sin omega t, as we know, inverse Euler gives us is equal to 1 over 2j e to a j omega t naught t minus e to a minus j omega naught t. So it has a coefficient. It has coefficient a1 equal to this 1 over 2j, and a minus 1 equal to this minus 1 over 2j. And so you can plot its big S over j omega naught. Big S over j omega, and it has two spikes, one of them at omega naught, and its height 1 over 2. Its height pi over j because you need to times 2 pi, and another one has this minus omega naught, and with height pi divided by minus pi divided by j. And similarly for cosine function, for cosine omega naught t, it's also periodic with period 2 pi over omega naught, and you can read this as a linear combination of e to a j omega naught t and e to a minus j omega naught t, and with a1 equal to 1 over 2, a minus 1 equal to 1 over 2. Then you have this spike with the area pi at omega naught, and area of spike of area pi at minus omega naught. Okay. Any questions so far? So you see that we see that for periodic function we can also write down its Fourier transform, and the Fourier transform will be summation of these impulse functions with impulse placed at k omega naught, and height will be proportional to the Fourier series coefficient ak. Okay, so height equal to 2 pi ak, and the position at k omega naught. So it will be the spike will position at the integer multiple of omega naught. Okay, and it will depend on what k has non-zero ak. Okay, and then we have a very interesting function signal to talk about. Okay, the signal has actually many applications, although we will not touch it in our course. But it's nice to learn, and it's impulse trend. It's a very symmetric signal. I guess that's easier to see. It's easier to see the signal. Okay, so the signal look at this is a whole bunch of impulse with equal height. So this is the impulse trend, and a whole bunch of impulse with equal height and equal spacing. So it's a very periodic signal. It's a fundamental period. So it's 1/t here that keeps repeating itself. Is the impulse trend. And it turns out that its Fourier transform looks exactly like itself with a bit different parameter. So if Fourier transform this thing, and it will become another impulse trend. So it's still equally spaced out and same height, and but the spacing here will be 2 pi over big T. Okay, and the height will be also 2 pi over T. Okay. And yeah, so this is a very interesting result. So we have this periodic impulse trend here, and the Fourier transform to a periodic impulse trend here. And also, this is a Fourier transform pair, so you can also inverse Fourier transform back. So you see that you transform, you have this periodic impulse trend on frequency domain, and you inverse Fourier transform back. You also get this. You also get this periodic impulse trend. And another interesting thing to see here, so I just saying a result first, is that you see this is 2 pi over t, and this is t. So if the period here gets larger, so t gets larger, then the period here actually gets smaller. Okay, so this is consistent with the property we said before. So if you stretch out the signal on time domain, you will compress the signal in frequency domain. So this is about 1/t, and this is about t. And if you squeeze in the signal, so you have a t smaller, then the signal here will stretch out. You have a larger one. If t is smaller, then you will get a larger 1/t. Okay, so that's the impulse trend. And anyway, now let's go. That's some description on impulse trend, and let's go back to a bit of the derivation here. So we want to write this impulse trend as a formula, then you can write this is a whole bunch of impulse. So for the delta function position at those periodic points, that's kt for integer k. Okay, at each big T, each integer multiple of a big T, you have an impulse. So at kt, where k is integer from minus infinity to plus infinity. You sum over all the integer k. And yeah, so this is a periodic function with the fundamental period big T, and then we can find the first we find this Fourier series coefficient. So we do the things in chapter 3. So this is the analysis equation in chapter 3 we have, and ak equals 1/t integration over one period, x over t e to the minus jk omega naught t. Okay, so you do integration over one period, so we take the period from minus t over 2 to t over 2, and in that period you only have one impulse, that is delta of t, then you have e to the minus jk omega t. Okay, and you see that this integration, the delta function will peak out small t equal to 0, so this exponential become 1, so this integration is just 1/t. And so, but this is 1/t, but this is ak, and so you see that for every k, the value doesn't change here. So this ak is constant for every k, just 1/t for every k. And then we back to the thing we just talked about today. Then we have that big S over j omega equal to 2 pi ak delta omega minus k omega naught. And yeah, so we have thing one by one. So 2 pi over ak is 2 pi times ak is 2 pi times 1/t, so 2 pi over t. Then summation of those delta function at k omega naught, and omega naught is obviously 2 pi divided by big T. Okay, and so k times omega naught with 2 pi divided by T. So here, yeah, 2 pi divided by T. So the spacing is omega naught equal to 2 pi divided by T. Okay, so that's imposition. People, is any question or derivation and things? Not, I guess we can stop very early, but let's just show a little bit. I guess next time we'll try to talk through some property of the Fourier transform. You can see that they are mostly very similar to the periodic case, I guess, except the differentiation. So we can show very quickly, say we have a linearity that we already used, but anyway, it's very easy to show. We don't have proof here. You just plug in a formula, you see you have linearity. And then we have like time shifting, example, and conjugation. We will probably go through very quickly through conjugation because it's just very similar to the periodic case. As you see here, you conjugate your x of t, then you get conjugation and the minus sign on your omega. That's just similar to when you do conjugation on x of t, you get star on your ak and the minus sign on k. Okay? And then we have the same real analysis, and we have the time symmetry analysis saying that the x of t is even, and big x of j omega is even, etc. So that's conjugation, and yeah, and we have more example, and yeah, differentiation will be different. So that's for next time. Okay, and I guess let's talk a bit about scheduling of the course. So next week we have a class on Monday, and there will be spring break, so no class on Thursday. And schedule the next week should be midterm. Okay, and so next week I guess we will try to finish some properties on Fourier transform and have a bit of a review, and then you can go to your spring break, and then we have our midterm. Okay, so yeah, that's the schedule. And if no question, then I guess we can stop now, and yeah, see you next Monday.